So it's week 5, 5-1. We started talking last week about fluid dynamics, moving fluids. First talking about static fluids, fluids in a container. Seems like an oxymoron that you could have dynamics for fluid statics or statics in fluid dynamics. But what we mean by accelerating fluids in a container is that they don't actually circulate. You move the container as a function of having that container move. There's some extra forces added, and we talked about how those would be both in linear acceleration as you shift it. The example with the oil cars, why you might want them flared at both back ends because of the headspace, and also rotational fluids. We used the expression that we have for forces acting on a packet of fluid both in linear acceleration and then in rotational acceleration to be able to define the forces that were applied. Yes. I don't want to do that. I want to go back, but I guess I can't go back. Well, that's fine. I'm going to stop that. And so we talked about Bernoulli's equation, which allowed us to be able to say something about how fluids move when they move along a streamline. In 4.3, we also talked about rotational acceleration. So what we'd like to do today is recap maybe the main points from both those two key discussions we had. One about fluids along a streamline, and secondly, fluid pressures, how they vary normal to streamline. And then we'll talk today about free jets and continuity and try and apply Bernoulli's law to be able to quantify some problems that we'd like to know something about. So just to very briefly recap what we talked about, most of the work we'll do is to define behavior along a streamline. And so that streamline could be, for instance, something that goes, and we've drawn this a couple of times, around an airfoil, not a very well drawn airfoil. But the idea is that along this streamline, we can define behaviors along its length, and we can write conditions at an upstream and a downstream location. And we know from Bernoulli's equation that we can sum up all the components. Some parts we haven't talked about yet. We know that the magnitude of the Bernoulli expression is constant along this streamline. And so we could write it at 2 points, and the components should be equivalent to each other. We know that for Bernoulli's equation, I guess I might as well could make this full screen. We know that for Bernoulli's equation, the requirements are, one, that it is incompressible. Two, it's irrotational, so no eddies, let's call this. No eddies. And the third one, perhaps the most, well, there are four, it's steady state. And the most important one is it is inviscid. In other words, dynamic viscosity or kinematic viscosity approaches zero. If this is the case, then this certainly is completely true, in which case we can write it between an upstream location. So by convention, we always write it upstream on the left, downstream on the right. It doesn't matter, of course, if it's inviscid because we don't have any other terms. But if there are viscous losses, what we'll find out is that we can add those viscous losses somehow in here. For now, we don't need to worry about those. These are zero. Also, as part of it, we could actually put in a pump and add energy to the system. So in other words, we could put a pump in at this location. So that would add energy into the system and going upstream to downstream, or as a turbine could take energy out. And for now, we're assuming that this is also equal to zero. So these are the terms that we don't deal with. So if we do that, if we ignore viscous effects, then all of a sudden what we can do is we can write it just in terms of pressure head, velocity head, elevation head, upstream, and downstream. And it's probably worthwhile doing that just by convention because it carries through for the cases where we will talk about viscous losses. So viscosity adds these extra terms which for now we're going to ignore. Incompressible is kind of a paper tiger because we've actually used it. We will use it for examples where we do it in air, such as for an airfoil. Could be in water or air, but we'll use it in air. And air definitely is compressible. I guess the other important condition is for us to think about is steady state and how we look at this. And so I've drawn this aerofoil as it is now, and of course the view that you'd have here, you could choose two viewpoints. You could choose a static viewpoint where the plane goes past you, and therefore the airfoil migrates past you in a static fluid. Fluid velocity is 0, but the plane is migrating. Or you could attach yourself to a seat that sits on the wing, and you could move with the wing, in which case you'd be traveling at the velocity of the plane, and the 0 velocity of the air outside would actually be whistling past you at the same velocity that you're going at in the other direction. Right? And so the first condition, where you're looking at the plane go past you, is not steady state to you as an observer because it's moving. You look at that scene all the time. The wing's here, then it's here, then it's here, then it's here. If you take a picture of that, then it's changing with time. If you're sitting on the wing, then it's definitely steady state because this is what you see. You see always at this point, at all times, the velocity is some number, v1, along the streamline. And always at this point, it's equal to v2, and it's the same. And so steady state matters because I guess it matters in terms of how we choose our frame of reference to be able to look at it. And so we'll always choose this frame of reference where steady state means that if you take a picture now, you have a picture, a map of the velocities all around this structure. You take a picture 10 seconds later, 100 seconds later, those velocities in those locations are identical the same. Won't be the same air particles moving through there, but those velocities will be the same. So these are the two probably most important ones for us. And we've talked about what it means. In terms of behavior normal to a streamline, if we do this, if we, let's see, if we use the example of some kind of feature that looks like this, and we could, if we look at the streamline going across here, look at how it goes in this direction. This would be, for instance, the velocity at this point, but also parallel to this, there'd be another streamline, nearly parallel to it. And so what we could do, look at it, in the same way as we talked about slinging a weight on a string around our head, if we wanted to, we could look at, for instance, this curvature that we have here, that going in this direction, the velocity along the streamline at point 1, these velocities are always aligned along the streamline. They're not normal to the streamline because, of course, normal to the streamline, by definition, the velocity is 0. And so this has a velocity here, and that would be this velocity, and it would have some curvature attached to it, not unlike our spinning fluid in a cylinder that we talked about a week ago today. And in doing that, we have one other feature. I'm going to make this bigger so maybe I can draw on it. And that normal to this streamline we have a normal. And since in our geometry we always draw z as positive upwards, then this is the Bernoulli term as we go across the streamline. You'll see that it has the same components, a pressure head, a velocity head, and an elevation head, which are here. But it defines the behavior in terms of how fluid pressures would vary as we go normal to this streamline. And so the important components that you'd have seen from 4.3 are that if the direction of z, which is positive upwards here, align with n, then the dot products, those vectors are co-aligned in the same direction. If you think of this as being vertical, not as a tilt, but being vertical, then this would actually be, you could replace this as dz and do the integration. And really all it's saying is that there's an extra term due to pressure that changes with depth due to the fact that you're going around a curve. And you can imagine driving a car, you go into a bump, you feel yourself, before the bump kicks you up, you feel yourself going down because you're pushed into this curve. If you're being pushed in a centrifuge, you'd be pushed into this barrier here, and you'd feel gravity which was higher than you experience. Conversely, as you go across the top of this, then the radius of curvature now, n, is in this direction. N is equivalent to negative z. Here, in this condition, n is equivalent to positive z. And so that'll just change the sign of this. And so what it basically gives you is it gives you a behavior which adds a component, if you like, due to gravity. And so you could write this expression here, and I'm going to do that. Pressure plus density. I've got an integral, don't worry about the integral. The velocity along the streamline squared divided by its radius of curvature. dn plus rho g z. Right? That's this term here. And so what we could do is we could write this together, and this is constant, which means that we could write it upstream at P1, V1, and Z1, etc. But if we wanted to, we could rewrite this by just gathering these terms on the left-hand side, which say that P plus, I'm going to take density outside, and then I'm going to add these as an integral v squared over r. I'm going to write this as, instead of z, I'm going to write this, sorry, instead of n, I'm going to write this as dz. And the integral of this dz is just z, so I can also write this as pressure plus density multiplied by v squared over r plus g and multiplied by z. So all I've done is integrated this. The only thing that integrates, if we assume that velocity is constant as you go across the streamlines, is this z. And so the important thing is that now that we have a component of pressure which varies as we go down, which is just additive of z. In this particular case, n and z were in the same direction, so this applies, and this term here is positive. So in this particular case, going around here, gravity would feel larger than it would be. If the velocity we're moving at is 0, then we just feel gravity at its normal magnitude. If it's larger than 0, this is always positive. Well, it has to be positive because you're squaring it. It's adding to it. And so at location 1, if you like, this is constant. This is location 1. And if you write it at location 2, all that will change is that because n and z are opposite each other, z is upwards, the radius pushing into this curvature here is directionally opposed to it, 1 to 1. The dot product would be minus 1 in that particular case. Then this would be minus. And I guess I'll draw, since the green one, I'll draw as positive. So That's what these two mean. And so it makes some kind of sense. It means that when you go over the bump, you feel lighter than gravity, and therefore the fluid pressure changing with depth would be less than the unit weight of the fluid. As you go into the curve at the bottom, because it's additive, it adds to it. And so that's really all the behavior across streamlines is telling us. So that's a simple way of thinking about it. So don't get derailed by that. So we can measure fluid pressures along streamlines, but that's by far the most important thing that we'll do in this class. We can also measure behavior across streamlines. Sometimes we need to know that. But the rationale of it is just this behavior of this centrifugal force, centripetal force, this acceleration here. But it still comes from F equals ma, as we know. All right? Okay. So that's a recap of what was on 4.3, basically. All right. Let's see if I can go back to where we were. Is this the one? Yeah, all right. So what we're going to do today is we're going to use the idea of free jets. And so this is a useful exposition of that. You could imagine some things we'd like to be able to calculate from this. For instance, you might want to size the pump which is driving this, in which case you'd need to know exactly what kind of velocities you'd have to come out of here to be able to hold a body above the ground. Whether you'd have to use a larger pump to lift it higher. You could imagine that that could be the case. How do we do that? And we can very simply use what we have so far in our toolkit, which is Bernoulli's principle, defined along the length of a jet. If I can pull it back to this. So basically here you have kind of a reverse fountain. You have this umbilical, which is has a pump in it, supplies fluid up to the top of here, and then squirts down, and it's this squirting of fluid that comes out of here that ultimately impacts the water that controls the navigation of this guy as he zips around on this. And so how do we look at defining the behaviors that control that? So first things first, let's look at using Bernoulli to be able to solve a problem, in which case we always keep the reference frame static. So Pitot tubes, okay, so it's been done. Yeah, I guess I was doing this. So you may be, no, you're not too young for this, 2009, I believe. So it was a plane that departed Rio de Janeiro for Paris, Air Flight 447, went through a thunderstorm across the eastern coast of South America, off Brazil, and never reached its destination, tragically. It was in the Atlantic, a very deep portion of the Atlantic. The black box was ultimately recovered, but at the time it was a mystery. Ultimately, it was pinned down to the fact that the navigation systems, which for planes is still done through a Pitot tube, froze as it went through a very cold cloud. The orifice got frozen by frozen water, and therefore it couldn't work. They couldn't define exactly the local velocity separate from the GPS, and therefore made some bad decisions about flying it and stalling it, and basically flew into the ocean. And so it's kind of interesting that even in this day and age, Pitot tubes have images, which are the things that if you climb onto a plane at University Park, you'll see them close to you climb on through this door and you're close to it. But all it is a front-facing piece of tube that is hollow, that has a pressure transducer at its base, and it has a central tube, a separate tube on the outside that allows you to measure pressures both at this tip, but also along the side of a separate tube. And by using Bernoulli, you can separate the magnitudes of the fluid pressures that you measure out here to be able to determine what it is. So again, it takes this concept of a steady state. So in reality, the tube is moving through the air is static, but you can choose to be the pilot and be sitting on top of the tube and looking at the air moving past you at 300 miles an hour, 600 miles an hour. There's an interior tube, which is this red one, and there's an exterior tube, which is this green one, and they both measure two different things. This tube here, by definition, if you write the behavior for this tube, then it would be Z2, I guess, Z2 plus P2 over gamma plus V2 squared over 2G. And you could write that as being equal to, for instance, the behavior at point 1. So at point 1, the behavior would be Z1 plus P1 over gamma plus V1 squared over 2G. And we just have to figure out what are the things that we know here. We know that, well, these Pitot tubes are almost always horizontal. And so Z1 and Z2 are the same. Even if they're not horizontal, they're basically the same. And so we can get rid of these two terms here. By definition, the velocity here, because it stagnates, it stops because it can't flow out of this tube. So if you measure the pressure at the top of this tube, it's exactly the same pressure you measure here, and it's due to the fact that you're killing this velocity of the air, is that the velocity at point 2 is equal to 0 by definition. And so if we measure this, we have a chance to be able to do something. The velocity at this point, since the air is just going over the top of this tube, is actually going to be roughly the same as this if it's a nice sharp tube. And so this is what we'd like to know. And if we're not accelerating or decelerating the air here, the pressure we have here is just going to be atmospheric, which is, if you use gauge pressure, is equal to 0. And so all that we need to get out of this is the fact that if we know the fluid pressure at P2 is equal to V1 squared over 2G, and if we just rearrange that to multiply both sides by rho G, which gets rid of this, get rid of this, we have that P2 is equal a half rho V1 squared. And so really what it is the difference. P2 is going to be the overpressure at this point. P1, we could leave P1 in an atmospheric if we wanted to, in which we'd have a difference between them. But if we measure the overpressure that occurs due to us stagnating the fluid at this point, making it stop, it gives us a way to measure this and to calculate what the velocity is. Obviously, if this fills up with water and it's clogged, then the pressure you get in here is wrong, and therefore you misjudge your velocity. You'd underestimate it, right? You'd be going much faster. It would tell you you're going at 0 velocity because it would lock in a low pressure, and it would allow you not to be able to calculate your true velocity. So that's how Pitot tubes work. It allows you to measure pressure difference between a couple of locations, and from that calculate what the local velocity. Nothing more. So in all the work that we do, what we'll want to be able to do is we have 6 terms here. We want to be able to write the behavior appropriately at those at 2 locations, and figure out which one of these 6 terms we don't know if we know all the other 5. Turns out that we can also do it if we only have 4 terms. We'll talk about that later. What would we expect the behavior to be if, at this point, where we're hoping to be able to measure a nice fluid pressure which is equal to atmospheric pressure, right? We'd like it to be untainted by the fact that we're moving through the air at 500 or 600 miles an hour. What would the conditions that we want locally at that particular spot? Well, if it was particularly badly engineered, so we had a lip on the downstream side, you can imagine that the fluid velocities hitting here would go from V at this point here to V equals 0. And if that's the case, then we'd basically be taking this term here so that we'd end up with an excess pressure that results from this deceleration. If you think about it, it's the same as being hit in the chest by a fire hose. The reason you feel that in your chest is because the stream of water in the fire hose has some momentum, v squared over 2g. You're taking that momentum and you're changing it very quickly to zero velocity, and it's that change of momentum that you feel in pushing you backwards. It's no different from air in hitting this lip. If you had the converse behavior in this, that you had a lip that did this, from the same rationale that we just talked about in terms of looking at pressures as you go across streamlines, what we drew before was basically this diagram here, that there's a radius of curvature, and that because of this radius of curvature, if you're swinging a cup around on a string, then it pulls some force out of you. It pulls your hand with some force, and so you're having to pull in here to be able to do that. And so the net effect of that is the pressure change as you go up here is reduced because it's being on an outward angle. From exactly the same term, the term we talked about before, which was v squared over r dn, we called it, right? This is the centripetal force term. And so this probably isn't a very good outcome either, but the best way is to have a nice smooth transition. You go right across the top here. You don't change the velocity of the fluid. It barely sees this back lip, and so the velocity here is the same as the velocity here, which is the same as the velocity here. If there's no change, then you'd just be measuring atmospheric pressure at whatever that elevation is. And the reason for having these two ports, I kind of glossed over it, is that you'd like to be able to, the pressure you measure atmospheric is going to be the atmospheric pressure at 30,000 feet, not at sea level. And so you'd want to be able to measure the true atmospheric pressure at that elevation, because the difference between that true atmospheric pressure and the fluid pressure at 0.3 or 0.2 is going to be the destruction of velocity, which will give you the speed of the aircraft. So, always interesting that such a basic piece of equipment that's been around, I think, for 100 years or more, is still what's used in aviation, despite GPS and satellite navigation, to give very fine. Of course, satellite navigation tells you how fast you're going globally, but if there's turbulence where you are, it won't give you the local airspeed relative that's important in making your wings do the things that you like your wings to do. You could use the same principle by by looking at directional Pitot tubes. You could imagine that you could also say something about the direction which the wind was coming by this little experiment. If you take a Pitot tube that's originally looking horizontally, then you could use it directly to be able to calculate the fluid pressure by looking at whatever the pressure head is, and the part in excess of the pressure head that's killed at this point by killing momentum is the velocity head that comes out of it. If you take that tube and you move it 90 degrees so that it's pointing, well, you couldn't do it pointing downwards because all the liquid would fall out, but you could have it pointing upwards, then all of a sudden the air going across the top of this doesn't change its velocity at all. So it would measure zero velocity. So if it measures a maximum velocity in the direction of flow here and records a velocity head due to that, if it records a minimum velocity at this point when it's parallel to this tube, and it would measure this velocity head equal to zero, you could imagine as you range it between the vertical to the horizontal, it would change, slowly increase. And so you could imagine a contraption like this little thing here that measures the velocities at a variety of different points, and you could imagine that if you look at the place where the fluid impinges on this, this is where the maximum change in velocity from a big number to zero will occur, and the fluid flowing around here will have smaller velocities. And so you could, if you oriented and measured the fluid velocities or the pressures at these individual ports, you could triangulate to tell the direction in which the fluid was coming from. And so you could you'd be able to define behavior based on that. So I think an oddity, but something that you could imagine doing. So we said that when we apply Bernoulli's principle, that we always have these 6 terms, 3 on the upstream side and 3 on the downstream side. And so we can only get one unknown from that if we know all 5 other terms, whatever that unknown would be. And that's what we've done here. We measure the pressure and we calculate the velocity using the Pitot tubes. What we can use is the concept of continuity to be able to do that. And so the concept of continuity is just this. We have a streamline which could be along the base of this channel here. The green could be a streamline, but this could also be a streamline. The top of the channel could also be a streamline. And if we box this off to be able to write that the flow velocity at point 1 multiplied by the cross-section at point 1 is equal to the volumetric flow rate. Likewise, we could draw at this point here a slightly different cross-sectional area, A2. And if that has to be the velocity V2 that's coming out through this, V1 here and V2, then A1 times V2 has to equal the volumetric flow rate. Length over time, length squared, so meters cubed per second is the volumetric flow rate. We know, because it's steady state, that we're not accumulating fluid, that what comes in through the upstream part has to leave through the downstream. And so we know that Q1 equals Q2. And so if we do that, then we can take both of these expressions and we can just write V1 A1 equals V2 A2. And so our interest in being able to do that is we can now define the velocity that's upstream is just the downstream velocity multiplied by the ratio of the areas. And so if we wanted to, we could substitute this into Bernoulli's equation for this term here to write it in terms of V2. And now we've taken care of one of our variables. And so in some cases, we can solve problems where we only have 4 variables because by continuity, we can make sure that we have a relationship between the upstream and downstream velocities. They don't have to be equal to each other, but they have to be related to each other by the ratios of the cross-sectional areas. And it's an important concept for us to use because it allows us to solve problems that we otherwise couldn't do because we only have 4 knowns and we want to solve for 2 unknowns. Can't do that. This allows us to take care of one of those unknowns, and you'll see us do that. Okay? So that's just a technique that we'll use. Free jets. Free jets is perhaps the simplest exposition, if you like, of Bernoulli's law. Again, all of it relies on us being able to write conditions at some upstream and downstream location. If we do it for this tank, so you take a big tank that has a small hole in the bottom, in the bucket, the basic question is, how quickly does water come out of the bottom? Very simple question. You could imagine it being the jet lev, except in the jet lev something is being squirted out under pressure, but it's a very similar idea. You hold a bucket, you get a stream of fluid coming out of it. How quickly does it come out? So what we can do is we can use Bernoulli. We can draw a streamline. Fluid has to flow from the uppermost portion here down along this line until it emerges here at point 2. If we calculate the 3 components for Bernoulli, we have, I always like to write it in terms of these length components. These are the 3 variables. So in this particular case, and we can do that So this is for point 1. We're going to write the same for point 2. P2 over gamma V2 squared over 2G and Z2. And we just need to define what they are. Sits on the free surface. Atmospheric pressure, same as we feel here. If we take atmospheric as gauge pressure, then it's equal to 0. If we work in absolutes, we just have to use absolute pressures. Much easier to work in gauge pressure. Big tank. You'll see this in the questions you do. A big tank means that this surface area is very large compared to this. So even if this is gushing out here, because the volume of the reservoir is large, it doesn't get drawn down very quickly. If it doesn't get drawn down very quickly, then we can take this velocity at the surface to be equal to 0. So if you ever hear the term, the tank is large, big reservoir, that's physically what it means, is that you can get rid of the velocity on this surface. It makes life much, much easier. We can choose a datum that's anywhere, and if we choose it at point 2, then this value here would just be the height above it, and that defines behavior. So we know everything at the upstream location. Downstream location, what's the pressure? We've made the point that the pressure at a point is always the same in all directions. So if we look at this point here, the pressure acting horizontally has to be 0 because it's atmospheric. And if we go across here, it's on the same elevation. So we can make the case that the pressure here, because it emanates from this tank, is gauge pressure, which is equal to gauge atmospheric pressure, which is equal to 0. This we don't know. And if we've taken our datum as 0 here, we have this. So the only thing we don't know is this. And so if you write Bernoulli in this way, this is a little different from these equations, but you can do it either way. You'll find out that we only have, well, we have only 2 terms, right? We have, yes, sir.
I don't understand the pressure part. How is 0?
The pressure, if we're standing here outside this, if you're standing next to a jet, air pressure has to be 0, right? If you look at pressure acting at a point, then the horizontal pressure and the vertical pressure have to be 0. So the fluid pressure acting on this jet here on the side, in the jet and outside the jet, has to be 0 horizontally. And if we say that pressure acting at any point has to be the same in all directions, then the 0 pressure in the horizontal direction here has to be equal to 0 pressure in this direction because of this. Okay, good question. Okay. That's the reason. And so if we take this as equal to this term here, so we can write H is equal to V2 squared over 2G, which just becomes 2GH is equal to V squared, which becomes V is equal to 2GH, square root 2GH. Standard result. This here. And you can see it elsewhere on that page, but it's important. And so it comes from those maybe manipulations, but just understand. Big tank, velocity is 0. Atmospheric pressure, pressure is 0. Elevation, it's not moving, static. Elevation, choose relative to some datum. You could choose the datum here, and this should just be negative z, negative h, right? But it's easier to take it at some other location. The rationale for velocities being 0 at this point, the pressure being, sorry, the pressure being 0 at this point, not velocities. The velocity is what we want to solve for, and the elevation we have. And so the standard result is just this. See at the bottom. What happens as we go down? We could also write this expression. Don't need at 0.5. What would happen if we wrote this expression at 0.5? So we, again, the pressure at 5 would be equal to what? Thank you. Velocity at 5? Don't know. And the elevation at 5 would be equal to minus h. And so what we could do is we could write Bernoulli between 0.1 and 0.5. And we could solve it. I guess we could do that right here. I'm running out of a little bit of space. Well, why don't I do it? Just because it's instructive. So if we do that, what do we end up with? We end up with z1 plus p1 over gamma plus v1 squared over 2g. And it has to be equal to the behavior at z5 plus p5 over unit weight plus v5 squared over 2g. What do we know? Relative to our datum, this is equal to lowercase h, but this is equal to uppercase minus h. Right? H is minus negative because it's below here. Pressure 1, still 0. Velocity 1, big tank, still 0. P5, same argument as before, 0. V5 is the only thing we solve for. If we rearrange the two h's on either side, we get h plus h is equal to v5 squared over 2g, which gives us ultimately the velocity at 0.5 is equal to 2g, the sum of those two heights, square root. So all it says is that actually it doesn't really care where the output of the container is. It just takes the sum of these two components. And it's no different really than dropping my blue ball that I like to bring to class. I drop it from the height at the beginning of the top of the tank. The velocity that ball would be traveling at as it gets to 0.5 would be given directly by that expression here. And it's no different from the velocity of that water. Yes, sir?
Is the pressure 0 because the bottom of the tank's open?
The pressure is 0 because if you think about this jet, yeah, sure, yes. If you close this tank, the pressure would not be 0 in there. But we're talking about by the side of this jet. I think an easier argument to make is that if you think of standing right next to this jet, atmospheric pressure is 0 by definition. Atmospheric pressure is 0 at this point, and it's 0 in all directions. And so if you take a point just inside this jet in the liquid, the horizontal pressure for equilibrium, pressure acting horizontally is 0. In the water acting against it is 0. It has to be 0 horizontally in the water. And if it's 0 horizontally in the water, it has to be 0 vertically in all directions. That's the reality.
Why does it have to be in vertical as well?
Because we know that pressure at a point is always equal in all directions. So if it's horizontally at 0, then by definition, in all other directions, it has to be 0 as well.
Is that always hold true, or is this a simplification of something further? I have a hard time wrapping my head around it.
It has to be true as you go. If you imagine that your jet is 10 miles wide, then as you go into it, you'll start feeling pressure. It'll be true as the jet becomes vanishingly thin. So you can think of it that way. It's a decent assumption. Trust me. Go ahead.
If you take a point near or like almost touching the wall of the, I mean, is it a container?
Yes. If you take the pressure here and get closer, what do you think the pressure would be at this point? I think it would be P is equal to gamma H. If you close it, I mean, you could do the mental exercise. What do you think the pressure would be if you close it? Actually, you can use Bernoulli with the velocity 0, and it will tell you exactly what the pressure is at this point if the velocity is 0. It'll tell you it's equal to this. If you open up, it will switch from being this to being 0. And so clearly as you go from this point here away from it, where it will equal this number, to going into the middle of this where it will be, I guess I'm not quite using the jet, but if you go into this point here, it'll switch to zero pressure. Clearly it goes through a transition. So I think perhaps the way to think about it is that if this is infinitesimally thin, then by definition, atmospheric pressure on the side of it has to give you zero pressure, and so it has to be zero. Don't make your life too complicated. Good question, so. What else? We won't talk about that. Oh, jeez. What else do you want to do? Anything? So if you look at last year's videos, as an example for the JetLev, which we won't go through today. We'll probably go through it in detail some other time. And also in terms of being able to calculate the power on a bicycle. Actually, we've got 5 minutes. Let's do it. There is no free lunch. You don't get out of here early. This is actually a very simple example. So this is kind of the world land record for riding a bike. And apparently, if you look down here, it's 60 miles an hour. This is the prone position, of course. Face here, butt here, legs here, cranking on something. And this is the velocity. And so you could also use that to ask, how much power does it take to push this bicycle through to be able to get this land speed record? And so you can do a very, very quick analysis to do that. And let's do that. So we have a bicycle. Let's think that our bicycle looks like this. Which of course it does. We know for Bernoulli it has to be steady state, so we're not standing here watching this bicycle go past us. We're going to attach ourselves to the bicycle, and we're going to assume that air comes past us at 60 miles per hour and hits the front of here. And so this is point 1, and this is point 2. And so we can write Bernoulli at these two locations, P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. They're both at the same elevation, so Z1 equals Z2. We know that in the air hitting here at point V2, we kill the velocity, stagnation point. But V1 is equal to 60 miles an hour, which is equal to about 30 meters per second. Factor of 2 difference. Just make life easy. We know that P1 is what? Atmospheric. We know that P2 will not be atmospheric. We'd like to know what that is. We know that this V2 is 0. And we're left with the expression that P2 over unit weight, rho g, is equal to V1 squared over 2g. Get rid of g's. What we'd like to find out is the force that's being applied to push this in this direction. The force has to be equal to the pressure multiplied by cross-sectional area. This is the cross-sectional area here. And so if you multiply both sides by a cross-sectional area, then this by definition, and multiply both sides by rho, and get rid of some terms, get rid of this, get rid of this. by definition, this is equal to a force. And so force is equal to V1 squared over 2 times area times density. Let's see if I'm very good at math today. Usually my math isn't so great. V1 squared, 30 meters a second, squared is about 900. So it's about 10 to the 1,000 meters per second. Meters squared, seconds squared, I guess. Area, well, let's take it as 1 meter. Smaller than that. And density is 1 kilogram per meter cubed, all divided by 2. And so the force, if we work that out, comes out to be 500. Is that right? 1,000 kilogram meters. Well, it's going to be watts. No, it's newtons. 500 newtons. I think. Is that right? Certainly, this is 1,000 times 1 kilogram divided by 2, which is 500 newtons. Hold on, this is the exciting part. Work is equal to force times velocity, which is equal to 500 newtons times velocity, which is 30 meters per second, which is 500, which is 1,500, which is 15 kilowatts. So you can calculate how much energy it takes to push a 1 meter sized piece of board through the air at 60 miles an hour. It ends up to be 15 kilowatts. If you look at the output for a human, it's something of the order of half a kilowatt, maybe 1.5 kilowatts at maximum extent. And so clearly it's not a meter wide at the front, but you can calculate that quite straightforwardly using Bernoulli. Yes?
Isn't that force per second?
Power, work. It's power, it's power. It's rate of doing work. Yes, you're right. Work would be force times displacement. Power is force times velocity.